Welcome back, where we're going to continue our discussion in chapter 10, and today we're going to look at how do we take derivatives of sets of parametric equations. So in the last video, we introduced the idea of parametrizing functions, the idea of taking a function and breaking the dependency on x and y in themselves, and introducing a new variable. We call that a parameter, and so that x and y are independent functions of t. And so now that we've done that, we see the benefits of it. Allows us to talk about directions, orientations, and different speeds possibly along a curve in the plane, where functions in the standard form, y as a function of x, don't allow us that manipulation. And since we were able to take a parameterization, the next natural thing to ask ourselves is, well, how does calculus work with sets of parametric equations? And so we're going to look at the derivative and how do we take derivatives of sets of parametric equations. And so I just reminded ourselves of what the derivative is. It's, maybe been a while since calculus 1. We take derivatives a lot, but we need to remember what the definition of the derivative is. And so the definition of the derivative is not all the shortcuts we learned, but the definition is a slope. Remember, the derivative represents the instantaneous rate of change. On a graph, the slope of the tangent line, in a practical sense, it could mean velocity, just an instantaneous rate of something. So an instantaneous rate of change or an instantaneous slope. And how do we measure that? Well, this is just the slope of a function for a small change in x. Remember, this represents the change in the y-coordinates, the change in the outputs of the function, over the change in the inputs. Delta x represents a small change in x. And so you're comparing the change in the y-coordinate to the change in the x. That gives you a slope. And you're letting delta x go to 0. So you're letting those points that you're measuring the slope with get closer and closer together. Therefore, then at the limit, measuring an instantaneous slope. That is what the derivative is. And then I also remind us just an alternate notation. Remember, we have our prime notation, f prime of x, we call it. We also have our slope notation. This is probably a better notation to use to remind us that it represents a slope, dy dx. Or what that really means is d dx of a function y. Y is a function of x, right? Y is f of x. And so this notation becomes a little more useful to us, and we're going to apply what we know about the derivative to now taking the derivative of a set of parametric equations. And so let's just go with what we know. We know that the derivative is an instantaneous rate of change of the y-coordinate over the x. Well, in this case, y and x are functions of t. So if delta t represents a small change in t, then I can represent the change in the y-coordinate instead of in terms of x, in terms of t. And so delta y over delta x, a change in y or a change in x, can be represented by f of t plus delta t minus f of t, completely in terms of the t variable, and f is the function for y. And g is a function for x, right? G, they're not dependent on each other, they're dependent on a variable t. So y is some function f of t, x is some function g of t. And so the change in the x coordinate is not just delta x, it's represented by some change in the function g. Same amount of change, right? G of t plus a small amount, delta t, minus g of t. And so a change in y over a change in x, a slope, for a set of parametric equations, well, we can write it just as we know here, except now y and x are functions of t. So we can express it this way for a small delta t change. Well, then the derivative would be the limit as delta t goes to 0, since these are functions of t, of this ratio that I just wrote down. The change in the y-coordinate in terms of t, and the change in the x-coordinate. This would now give me the instantaneous rate of change of a set of parametric equations in terms of the variable t. Now, this doesn't look like the standard form for a derivative, so it's not like I get something I know yet, because I have this ratio where I have numerator and denominator look kind of the same. But I'm going to manipulate this without actually changing it by multiplying this expression by 1. What will that 1 be? Well, very simply, I'm going to do it as 1 over delta t. 1 over delta t. 1 over delta t and 1 over delta t. Therefore, I've just multiplied by 1, so I haven't changed the value of this expression, the value of this slope. I just changed the way it looks. And so if I rewrite it now and I put that 1 over delta t into the numerator, it looks like this. If I multiply that 1 over delta t into the denominator, it looks like this. I put them in parentheses to get an idea of the numerator and denominator being separate. And although we have fractions within fractions, and it doesn't look like I've made it any easier, it looks more complicated, now we look at what the numerator and denominator are separately, and they should look very familiar to us. In fact, if I go right here, I notice that this limit is the definition of the derivative of this function. And so if I look at the numerator, well, this is then the derivative of f, when we take this limit as delta t goes to 0, except in the variable t instead of x. And so what does the numerator become when I take that limit? Well, by definition, the numerator would be f prime of t. The limit split up over numerator and denominator, so we take the limit of the numerator, take the limit of the denominator, and what do we get in the denominator? Well, that's the same exact type of expression just for the function g, and so we get g prime of t. So in terms of, instead of f and g, let's just think of the functions y and x. F representing the function for y, g the function for x. In our slope notation, this would be dy dt over dx dt. So what is the derivative of a set of parametric equations? It ends up being quite nice. It ends up being the ratio of the derivative of the y function over the derivative of the x function. Dy dt over dx dt. The change in y, the instantaneous change in y, over the instantaneous change in x in terms of the variable t. So derivative over derivative. That's a very nice result. Unfortunately, for us, when we take the second derivative, we have to be careful. We can't assume that this is a pattern yet. It's kind of, we don't want to make the assumption that we see the pattern already, or only doing one example. It's like if I gave you some numbers really quick and you think in your head, and I give you the number 2, 4, and I ask you what the next number is, you could give me 2 answers and you don't know which one's right. You could assume that I'm adding 2 and you would say 6. Or I actually could be multiplying by 2 and then the answer would be 8 for the next term. How do you know? Well, you don't. And that's because you don't have enough information. And so in the same way, yes, we know the derivative of a set of parametric equations ends up just being the derivative of the y function over the derivative of the x function. Dy dt over dx dt. We don't want to assume, though, that that extends to the second derivative. In fact, the second derivative is not the second derivative of y over the second derivative of x. That is not true. Okay, so we have to be a little more careful. But let's just put this into practice and let's just realize how easy it is then to take derivatives of sets of parametric equations. Say we have something like this. X is 1 over t. Y is t squared plus 2, and I ask you for the derivative of this set of parametric equations, dy dx. Right? Dy dx, the derivative of this function can be expressed, we just saw, in terms of the derivative of the y function over the derivative of the x function. And so if I look at the y function, its derivative is 2t. If I look at the x function, using my power rule, I get negative 1 over t squared. Fractions over fractions, let's multiply by the reciprocal, I get negative 2t cubed. And so this tells me the instantaneous rate of change at a given t value. And so when t equals 1, for example, what's the point we're given? When t equals 1, the x coordinate is 1, and the y coordinate is 3. So that's the point we have. When t equals 1, the slope is negative 2 times t, which is 1 cubed. So we get negative 2. So we have our point, we have our slope given a certain time value, and of course we can write the equation of the tangent line. Y minus the y coordinate equals mx minus the x coordinate, and we're all in good shape, everyone's happy. Negative 2x plus 2, add the 3 to the other side, I get y equals negative 2x plus 5. And that's the equation of the tangent line. And so we apply everything we know from calculus 1, except now with a given set of parametric equations. How do we do it? Well, the derivative ends up just being the ratio of the derivative of y over the derivative of x. So derivatives aren't that bad to take. Now we want to extend this because, of course, in Calc 1, you don't just talk about the first derivative, you also talk about the second derivative. And so let's explore a little bit for a second, how would we take the second derivative? And now we're going to try and understand the true pattern that's going on. So what about the second derivative? Okay, well, we just saw a second ago that d dx y or dy dx ends up being dy dt over dx dt. If I wanted to write this purely in terms of y, then I would really have this as d dt of y over dx dt. Because why do I write it like this? Is because when we're actually looking for the second derivative, we are really trying to understand this. The derivative of the derivative, d dx of dy dx. The derivative of the derivative. Well, what we ended up seeing as a result is a little bit more than dy dt over dx dt. It's really d dt of y over dx dt, where y is the function that I'm starting with. Here, I'm not starting with y, but I'm starting with dy dx. And so if I see the pattern for what it really is, then the answer is actually d dt of dy dx over dx dt. This is really the pattern that's going on, and I extend that here. It's not just dy dt over dx dt, it's d dt of y over dx dt. Y is the function we started with. We expressed it parametrically, and so instead of thinking about it this way, we wrote it in terms of variable t, and we end up getting this. In terms of my original function that I started with, well, we can think of it this way, and we can extend the pattern. That means the third derivative, well, that's the derivative of the second derivative in this notation. Well, that would be the derivative of the second derivative over dx dt. So the derivative, parametrically, there's always a over dx dt, and the pattern is actually taking the derivative of your derivative. Right? This should make kind of sense in terms of how we take derivatives. What is the second derivative? In the numerator, you see it is the derivative of the derivative in terms of t. Here's the third. It is the derivative of my derivative in terms of the variable t. Remember, we wrote our derivative in terms of t, so it makes sense to take the derivative of this. That is not enough, though. We divide it by dx dt. And so if we look at that last example, x was 1 over t, y was t squared plus 2, and we talked about what dy dx was. We ended up getting, if you remember, negative 2t cubed. Then what is the second derivative? Well, it would be the derivative of this derivative. So it's d dt of my derivative. So just take the derivative of this in terms of t, and that gives me negative 6t squared. That's the numerator. But then that gets divided by dx dt. And so now I need to divide it again by the derivative of the x function, which was negative 1 over t squared. And so the second derivative becomes 6t to the fourth. Multiply by the reciprocal. Negative, negative makes positive. Just to extend this pattern for a second, so let's just take the third derivative just for the sake of taking it. If I take the third derivative, it's the derivative of my derivative. So part of it is 24t cubed. Divided by negative 1 over t squared. And where do I get that from? Well, divided by dx dt. It's the derivative of the derivative divided by dx dt. And so my actual answer would be negative 24 t to the fifth. And so those become the derivatives. And this pattern now continues. And that is the true pattern that we see. And the pattern that is there. And so to extend this, right, this is my set of parametric equations. We could ask ourselves, okay, what is the concavity at t equals 1? Right, we measured, in the last whiteboard, we wrote the equation of the tangent line at t equals 1. Here, let's go and find the concavity. Well, concavity comes from the second derivative. And so I'm going to plug 1 into the second derivative. And we get 6 times 1 to the 4th, which is 6. That's positive, and so we are concave up at this point. So at the time 1, which ends up being the point 1, comma 3 in this function, we are concave up, and we know the slope is a tangent line. And so we can apply everything we know from Calc 1 now with derivatives, tangent lines, concavity, and just with a new way to take derivatives. And so there's not much more to be said here, because we're just going to be taking derivatives in the way that we do it normally. We just have to be careful of the process. So in terms of the variable t, if we write things out parametrically, we just have to be careful about how we take the derivatives, but we get the derivatives nonetheless. And so that's going to wrap up our just kind of brief talk on calculus, specifically pertaining to derivatives when it comes to sets of parametric equations.